Today, we barely think about how our devices talk to each other. You open a case, put in your earbuds, and the music simply plays. That same invisible link extends to the watches tracking our steps, the speakers on our shelves, and the keyboards on our desks. Because we don't see any physical cables transferring the data, this immediate, frictionless communication feels almost like magic. But there is no magic involved. This reality is the result of engineers spending decades trying to completely redesign how electronic hardware interacts. To understand the scale of that engineering problem, we have to look back at the 1990s. Computers and early mobile phones were rapidly becoming more powerful, but they were literally tied down to desks and outlets. Moving information meant digging through a drawer to find a specific cord. Different companies built their hardware with entirely different physical connectors, creating a chaotic, disorganized mess of wires for anyone trying to link a printer to a computer. Facing this growing tangle of plastic and copper, engineers started asking a highly specific question. Could everyday devices exchange data over short distances, using radio waves instead of physical cables? While radio technology itself was old, shrinking it to fit inside portable consumer electronics was a massive hurdle. A viable solution needed to be microscopic, incredibly cheap to manufacture, and drain almost no battery life. In the mid-90s, a team at Ericsson took on the challenge. They set out to build a short-range wireless communication system for personal gadgets. The pressing obstacle was power consumption. They had to design a radio transmitter that could reliably broadcast without killing a phone's battery. Because that low-power signal was weak, it had to survive in rooms heavily crowded with competing frequencies. But solving the physics was only half the battle. If Ericsson kept this new technology to themselves, it would only ever work between Ericsson products. So they approached major industry competitors, companies like IBM, Intel, Nokia, and Toshiba, to collaborate on a shared system. Convincing fierce corporate rivals to agree on the exact same method of communication ensured that a computer from one brand could seamlessly talk to a peripheral from another. This massive collaborative effort is where the standard got its unusual name and recognizable blue logo. The project was given a temporary code name inspired by a 10th century Danish king, Harald Bluetooth Gormson. King Harald was famous for negotiating peace and bringing competing Scandinavian factions together. The engineers saw their new technology doing the exact same thing for fractured electronics. Despite the grand historical parallel, early Bluetooth products were frustrating to use. Initial connections dropped constantly, data transfer speeds were painfully slow, and pairing required multiple failed attempts. Instead of scrapping the system, the engineering coalition spent years quietly refining the underlying code, addressing security flaws, and strengthening the connection stability. Innovation rarely arrives perfectly packaged. The massive global adoption of this technology relied entirely on engineers working through the failures of a very rough prototype. A critical turning point arrived when smartphones hit the market. Users suddenly needed their phones to automatically route calls and music into their car audio systems without fumbling with menus. To support this growing demand, the developers released an update, Bluetooth Low Energy, or BLE. This diagram illustrates how BLE operates. By allowing hardware to maintain constant wireless links using a tiny fraction of the power, BLE made it practical to build smartwatches, medical sensors, and always-on home automation systems. This specific update pushed the technology far beyond basic audio transfer. It became the invisible infrastructure connecting a massive ecosystem of tiny devices across the physical world. All of this complex infrastructure traces back to one specific, highly focused engineering goal: finding a way to get rid of the physical cable. By focusing strictly on that singular issue and continuously improving the standard, the consortium created a tool that billions of people eventually adopted. Ultimately, it worked because it drastically reduced friction. Users didn't have to learn a complicated new operating system. They just tapped a button and their devices linked. The truest measure of Bluetooth success isn't its data speed or power efficiency. It is the simple fact that we rely on it constantly and rarely notice it exists.